Hey everyone, I want to use this video to talk about continuous random variables. We talked about discrete random variables last time, and so I want to talk about continuous ones this time. There's not that much more to say about random variables in general, but I do want to touch on geometric probability, what it means to find the probability of using areas, because that's a thing that we do a lot. So anyway, let's get started there. So let me pop over to the notes. So I want to talk about continuous random variables, like I said, and so there's two specific ones we're going to talk about, uniform and exponential. We'll get to those a little bit later. The first thing I want to say is about geometric probability. So the idea of geometric probability, if you think back to the way we did probability before, it was like number of things we're interested in divided by total number of things possible, right? What's the probability of rolling an even number on a six-sided die? Well, there's 3 even numbers out of 6 outcomes, so it's 3 out of 6, right? That does not work with geometry because there's like an infinite number of points in even the smallest space in geometry. So what you do instead is this. The area of the thing that you're interested in divided by the total possible area. You just turn things into area, basically. This is not a particularly hard concept, but let's see a simple example to see how that goes. All right, so Bernice, the spiderling, is ballooning away from her mom's web. So what ballooning is, by the way, is some species of spider will, when they are becoming young adult spiders, I don't know if there's a term for that, they'll extrude some webbing and then not like pinch it off or let it go, and the wind will just pick them up and fly them somewhere. And that's how they go a long way to spread out, to get away from the web, right? Because there's too many spiders and not enough food in one place for an entire family of spiders. So they spread out like this. Now, when they do this, they don't have any way of controlling it. They're literally just being blown by the wind. That's it. And then where they land is where they land. That's their new home, basically. So Bernice here is ballooning away from mom's web, and she's going to land in a public park with a pond in it. So somewhere in this park. The park is 300 by 200 rectangle, and it has the pond in the park has a surface area of 9,000 square meters. So I want to find the probability that Bernice will land on dry land. So to do that, what we're going to do is, of course, draw a picture. All right, so let's draw this picture here. So we got park. Let's make this. Actually, let's put the pond in. Pond. So pond, and then park. Park will be green. That seems right. There we go. So Bernice, not being an aquatic spider, would like to land on the green part. So we know that this is 300 by 200, right? 300 meters by 200 meters, which is quite a park, by the way. That's quite a distance. And then the pond has 9,000 square feet of area. Square meters, excuse me. We're doing this in meters squared of area. Right, and so what we want to do is find the area of the green out of the total area. So the easiest way to do that, at least in my opinion, well, let me pause for a second and let you think about it. Okay, the easiest way to do that, in my opinion, is to find the area of the overall rectangle and then subtract off the 9,000 square meters. Right, so I'm going to do 300 times 200, so 300 by 200, I should have units on that, meters is 60,000, right? Yeah, 6 followed by 4 zeros, 60,000 square meters. Now that's ugly, but we'll live with it. So that means that the park, a subpark, I mean land actually. Oh, hang on. Getting the pencil back is surprisingly hard. A sub land is 60,000 minus 9,000. Everything is in the way of everything else. Pardon me. So many windows open. Minus 9,000. Which is 51,000 meters squared. So that is out of a total possible landing area of 60,000, right? Because the whole thing's 60,000. And she wants to land on 51,000 square meters out of the 60,000. So she's probably in luck, but not necessarily, right? So probability of land is 51,000 over 60,000, which is 17 out of 20, which is 85%. 85%. So probably, she's probably good. Hopefully she does not end up, in water and in bad shape. So we got 85% chance that she'll land on the green stuff. So again, I just want to emphasize the idea here is area you're interested in divided by total possible area. All right, that's basically all I want to say about geometric probability. I think that's really all there is to say about it, to be honest. There's not a lot to say there. So let's go back to the notes and see what we've got. All right, so what we're going to do eventually, like almost immediately, is this. We're always going to scale everything, scale all of our distributions to have a total area of 1 representing 100%, just like we did in just like we do in any other probability. We want all the probabilities to add up to 100%. So since we're thinking of probabilities as areas, we want all the areas to add up to 100% or 1. Therefore, all of our calculations are going to look something like where is it? Like this, where the denominator, total possible area, is 1, because that's all the probability there is. So that means that the probability of A is going to equal the area of A, right? So this is a really important idea in statistics. We're going to use this nonstop, like for the rest of the semester, and for any sort of statistics you do for the rest of your life. You want to think about this. Area equals probability. Like, that's a really important concept. Now, in general, depending on what your distribution looks like, finding the area you're looking for could range from incredibly easy, like in our first example, to a little bit medium, like the second one, where you have to actually use a formula and there's the exponential of it. You'll need a calculator. To incredibly, incredibly hard, like beyond the scope of this class hard. Luckily, we're just going to use a calculator for basically all of it, except for the first one. This first example here of uniform random variables, we're not going to use a calculator because it's so simple we don't need to. Like, it's the best reason to not use a calculator. Everything's too easy. So, so let's see what those look like. Uniform random variables are very specific. They're used in very specific circumstances where all the outcomes are equally likely. And when I say all the outcomes, what I really mean is we're talking about a continuous random variable here. So it's not just integers like it was with discrete random variables, where, I mean, technically it could be things that are not integers, but it's overwhelmingly likely that discrete means integers. Uniform random or continuous random variables have everything in a range. So there's not a finite number of outcomes. There's always an infinite number of outcomes, because we're thinking about every number between, like in this first example here, every number between 0 and 90 seconds, including all the fractions and decimals. And of course, time flows in a continuous fashion, at least as far as we know. And so you could be like literally anything between 0 and 90 seconds, right? 72.153 seconds is somewhere in there, and that's one of the outcomes. So you use a uniform random variable when all of the outcomes in a certain range are equally likely. So the classic example of this is a random number generator, right? If I asked Sheets to make me a random number, and I'm pretty sure it has random number functionality in there. I'd be surprised if it doesn't. Between, let's say, 0 and 1, it's going to give me any number between 0, any decimal between 0 and 1, and they're all equally likely, right? I'm not expecting like peaks and valleys in the frequency distribution of my graph. I'm expecting them to be all equally likely. And since frequency or probability is your y-axis, that means that every value has the same height. So what you get is something that looks like this, right? Where the probability is on the y-axis here, and the x-axis has the time. This is waiting time at a stoplight. We'll see in a second. So every time, the probability of this time is this height, and the probability of this time is the same height, and the probability of this time is the same height. right? So they all have equal probability. So anytime you have everything in a range being possible and also equally likely, you want a uniform distribution, right? So let's see what one of those looks like. All right. So stoplight at the corner of Carrillo and Cliff Drive takes 90 seconds to turn green. By the way, this is not at all how stoplights function. It's just a very simple example. Let X represent the time we have to wait if we arrive at the corner of Carrillo and Cliff while the light is red. So in other words, we get there and the light has been red for some amount of time, right? And if it's been red for 10 seconds, then we have 80 seconds to wait because it lasts 90 seconds every time. Or if it's been red for 84 seconds, we have 6 seconds to wait because it lasts 90 seconds. So this wait time, by the way, it reads a little bit backwards. Like if we're over here, if we have 0 seconds to wait, or let's say 1 second to wait, that means that we arrived very near the end, right? We arrived after it had already been red for 89 seconds, and now we only have 1 more second to wait. Or we arrived 10 seconds in, and now we have 80 more seconds to wait. That would be over here. So there you go. Everything on this graph is possible. Everything between 0 and 90 seconds. Like you arrive, it's red when you arrive, and so you have some amount of wait time. Like if you get there just as it's turning green, then you have 0 seconds. And if you get there just as it's turning red, then you have to wait for 90 seconds. And anything in between is also possible. Since there's no particular reason to think that any of these is more likely than any of the others, we treat it as though they're all uniform, right? There's no reason to think that you would get there at the beginning or get there at the end because you've just been driving around normally, which is, say, in a fashion unrelated to the way that this light is, to the progression of this light. So, a couple things. One, we're gonna have everything between 0 and 90 possible. And anything outside of that is impossible. Clearly, you can't have a negative wait time. And since the light is only red for 90 seconds, you can't have more than a 90-second wait, right? Even if you arrive just as it turns red and you have to wait the whole time, well, then you still have no more than 90 seconds. And that means that since we want the entire area of this distribution to be 1, that since the base is 90 and it is a rectangle, so the area is base times height, then we want the area to be 1, so the height has to be 1 over 90, right? The number that you multiply by 90 to get 1 is 1/90th. So it has to be 1 over whatever the length of the base is, which, by the way we're going to notate this is UAB, like this. Right, so U for uniform, and then AB for the left and right endpoints of the uniform distribution. So in this case, A is 0 and B is 90. So the way you find how long the base is B minus A, right? You just take 90, in this case, 90 minus 0 tells us it's 90 units long. If I had a uniform distribution from 20 to 50, for instance, then it would be 30 units long. And so the height would be 1 over 30. Right, it's 1 over whatever the length of the base is, so that the area is 1. So the mean is fairly straightforward here. It's right in the middle. It's also where the median is. The standard deviation is kind of interesting. It's b minus a over root 12. That is not a thing that I can explain to you unless you know calculus. So if you know calculus, I will be happy to show you how to find that. And if you don't, I probably can't help you because you have to. So everyone asks where the root 12 comes from. Almost literally everyone is curious about why 12. I'll show you if you know calculus. Otherwise, you just have to trust me. Yeah, so there's our notation. We're going to say that X is approximately uniformly distributed with left endpoint A and right endpoint B, and the mean is determined in terms of the left and right endpoints, and so it's the standard deviation. All right, so we want to find some probability. Now, this is the best part of uniform distributions. Probability is incredibly easy to find. It's all rectangles, right? So I want to find the probability that someone who stops at this light will have to wait more than 60 seconds. So I'm going to do that on a whiteboard. So I'm going to draw a picture. Not this whiteboard because I need some space. There we go. All right, let's move this around just a little bit. I don't know if you can see this or not on the video. I'm just adjusting things. Okay, so I'm going to use that picture I just had up on the other screen. I just want to be able to draw on it. So we're going 0 to 90. Right, so there's 90. Here's 0, and here's 1 over 90 as the height. And the question was, what's the probability that x is greater than 60? All right, well, what I'm going to do is find that area. So here's 60, about 60. So I am looking for this area. Let's make it hot pink. There we go, that nice pink area there. So the way I'm going to find that is by finding its area. Remember that probability equals area. So if I want to know what the probability of landing in the pink region is, I find the area of the pink region, and that's it. So this is a rectangle, and the base is from 60 to 90, which is, say, 30 units, and the height is 1 over 90, and so I multiply it, and then I'm done. Like that's literally it. So probability, oops, I already have that, don't I? Probability that x is greater than 60 is equal to, well, the length of the base is 90 minus 60. That's base, times the height, which is 1 over 90. And so this whole thing is going to be 30 over 90, right? Over 90, that's at 9, believe it or not, which is 1/3. There you go. That's how you find it. Now, you might say, well, wait a minute, Jeff. You said greater than 60. Shouldn't I start at 61? No. Because we go all the way down to 60, right? 60.00001 is greater than 60. So here's the thing. One thing that's a little bit weird about continuous probability is that if I did this, the probability that x equals 60, well, probability is area, right? So it's still area, and the width of this line is 0. It goes from 60 to 60. And so the probability that x actually equals 60 is 0. And this is a little bit of a paradox with geometric probability, or with continuous probability rather, which is that the answer has to be something, but every individual thing has probability 0. And then you add up an infinite number of zeros and somehow get 1, right? So this is a little bit, it's hard to think about this. But that is how it works. That is basically how it works. The probability of this thing is 0. Probability 0 in continuous probability doesn't actually mean impossible, doesn't mean literally impossible, but it's hard to describe what it does mean. And so I'm really not going to kind of try. So think about, like, if I land here, right? So this is what, 75 seconds or something, right? If I measure time finely enough, there's a whole lot of things right around 75 seconds, specifically an uncountable number of them if you're into math. And so we think about any one of them as having probability 0, even though the time that you stop there has to be some time, right? There's going to be some time that you stop there, but anyway, I'm just going to leave that as a little bit of a paradox. I have to say that I don't have a good conceptual understanding of it, right? I can explain the math. The math involves calculus and limits and things getting smaller and all that. But I don't have a good conceptual framework for that. I actually, 3 Blue 1 Brown has a really good video on probability 0 doesn't mean impossible. I will go ahead and link that in the module, and I'll let him explain it to you. He's a great explainer. If you've never seen his channel, by the way, I highly recommend it. But we're off on a tangent. For now, just realize probability that x equals 60 equals 0. So that means that the probability that x is greater than or equal to 60 would be the probability that x equals 60 plus the probability that x is greater than 60, right? But this thing is 0. And so those two things, so this, the greater than or equal to and the just greater than, are in this case the exact same thing. So when I say this case, I really mean continuous probability. This is not at all true with discrete probability, right? If you remember, one of the big things that we were trying to figure out, one of the difficulties with calculating discrete probability was figuring out exactly whether you meant greater than or equal to, less than or equal to. It was a big deal. Here, totally irrelevant, not used at all, because the probability of x being some number is 0 because it has 0 area. So that aside, here's how we calculate area, right? So in calculating area or calculating probability in a uniform distribution, it's rectangles. It's all rectangles. The area is all going to be like something like this, where since the uniform distribution is itself a rectangle, and we're just going to chop it up, we're just going to find various parts of it. Well, those parts are rectangles, so everything's easy. This is why we don't need a calculator. You can use a calculator if you're really like terrified of fractions or whatever, but it's not necessary. And if you go look in like the distributions menu in your TI calculator, you will not see a uniform CDF or a uniform PDF because it's basically too easy. So they don't have them in there. So I'm going to go ahead and erase everything. I'm just going to erase everything. That's the easy way to do this. And then redraw the thing again. So let's quickly go back to look at what the next question is. Find the probability that someone who stops at this light will have to wait less than 10 seconds. So same deal, right? So we're going to do the same thing, but instead of greater than 60, we're doing less than 90. You can probably actually do that one in your head if you wanted to, but I'll draw it. 0, 90, and we got 10 here, 10. Not super accurate. Obviously, I'm not being super careful about this. I want to find the fuchsia area. Pink fuchsia? I don't know what color that is. I'm a little bit colorblind. So we're going to go probability that x is less than 10 equals, well, the width of, so we're doing base times height again. So 0 to 10 is 10 times the height still is 1 over 90. So we have 10 minus 0 times 1 over 90 equals 1. Or about 11%. Simple. Okay, next one. I think I have a couple trick questions here. Yes. I want to find the probability that someone who stops at this stoplight will have to wait at least 60 seconds, given that they arrive during the last half of the time that the light is red. So I'll pause here and let you think about that. All right, so the answer to this question is 0. Because if they arrive during the last half of the time that the light is red, that's only 45 seconds long, right? It's half of 90 seconds. So they can't wait any more than 45 seconds. So this thing is, so it's not possible for them to have to wait 60 seconds if there's only 45 seconds of red light left. So this one's 0. This one's a conditional probability. I want to find the probability that x is less than 45, given that we know x is greater than 30. So if you think back to conditional probability is a restriction of the sample space, and it still is. So I'm restricting myself to only consider the times where x is greater than 30, and then within those times, I want to find the probability that x is less than 45. So if you recall, what we're going to do is, so let me go back to a window, or to a whiteboard here. Sorry, losing my train of thought there. So if you recall, we have probability of A given B is the probability of A and B over the probability of B, right? So we are restricting ourselves to B, so that's what goes in the denominator, right? We're only, like, this is our new sample space, is B. And then within that, we want to know what's the probability that we're in A, so it is all the stuff that's in both A and B divided by the stuff that's in B, right? And so the question here was find the probability that x is less than 45, greater than 45. I forgot the less than 45, given that x is greater than 30. X is less than 45, given that x is greater than 30. So I'm going to restrict myself only to this, like that's what my restriction is. And then within that, I want to know what's the probability of this. So we're going to find, this is going to be the probability that x is less than 45 and greater than 30, which another way to write that is that x is between 30 and 45, right? So it's smaller than 45, but bigger than 30 means that it's, 30 and 45, and x is somewhere in here, right? This is the probability that x is between 30 and 45 seconds divided by the probability that x is greater than 30. So those are the things that we have to find. Now, we'll make this really easy. Like, this is, I'm guessing you've probably noticed this, but the length of the base is just the length of the base is the numerator of your fraction, and then the denominator is 90 in each case. Well, the length of this base is 15, because it goes from 30 to 45. So this is 15 out of 90, which we could reduce, but I'm not going to. And then greater than 30, well, 30 is here, and 30 to 90 is 60. So this is 60 out of 90. Right, and so let me quickly erase this stuff here. So what I'm looking at here is really this. Whoop. Hello, whiteboard. There we go. So here's 30. So within, let's do the black. Within this, what's the probability of this? Right, so what portion of the black area is also pink, is essentially what the question is. Well, the pink area is 15 out of 90. The black area is 60 out of 90. And I don't know if you remember how to multiply fractions, but there's a good reason not to reduce these. So this ends up being, writing in pink. I mean, pink's fine, but I want it to be black. 15 out of 90 times, and then so what you do is you flip over the denominator, right? So this 60, instead of dividing by 60 over 90, I'm going to multiply by 90 over 60. 90 over 60, and then if we cancel stuff, right? The 90s cancel, 15 and 60 cancel to give you 1/4. So if you know that the light has been red for 30 seconds when somebody arrives, then what's the probability that they wait less than 45 seconds within that? It's 1/4, because 1/4 of this black area is also pink. So there's conditional probability for you. It's done the same way, right? So still the same formulas, right? The probability that x is less than 45 given that x is greater than 30 is the probability that x is between 30 and 45 divided by the probability that x is bigger than 30, right? So in other words, it's these two together, like this and this, divided by this, right? And so same idea for conditional probability. It still means the same thing. It's a restriction of the sample space. You calculate it very slightly differently, but not really that differently, right? We still use the same formula. It's just there's a bunch of geometric probability in the formula instead of discrete probability. So let's go back to the notes and look at those. Ooh, come on. There we go. All right, that was number 5. I want to find the average wait time and the standard deviation of the wait times for all the drivers stopping at this stoplight. Well, that's very simple, right? There's not much thinking to do there. That you literally just use the formula. The average is the mean. It's in the middle. It's going to be 45. We'll use the formula in just a second. Then the standard deviation is going to be b minus a over root 12, which is 90 minus 0 over root 12, which we can calculate with the calculator. So let's go do that. So number 6 here. Let's go back to the whiteboard. I'm going to clean off most of this. Just clear everything. So we know that mu of x equals 0 plus 90 over 2, or just the average. It's right in the middle. This is 45 seconds. And then the standard deviation is b minus a, so 90 minus 0 over the square root of 12, which is, I don't remember what that is. Like 25 seconds or something? Let's go look. So, I did not just pop the calculator up for me. You probably want to look at that too. So we're going to do 90 divided by the square root of 12. 25.98 seconds. There we go. That's all there is to it. You just use the formula. So 25.98 seconds. And you can be forgiven if you would like to round that to 26. That's fine. It's close enough. All right. Find the 40th percentile of wait times at the stoplight. Now we don't have a formula for that. We're gonna have to think our way through this one. So I want the 40th percentile. So I really asked this question to remind you what percentiles are. So let's look at what they mean. So if you remember the definition of percentiles, they are the cutoff point where, in this case, so the 40th percentile is where 40% of the data is to the left, it's smaller than that. And 60% is to the right. And so the 75th percentile is where it's 75% of data smaller, 25% larger, et cetera, et cetera. So the 40th percentile looks something like this, right? Now, I've basically asked this question I asked it backwards from the other things. What I've done here is I've actually told you what the area is. When I say 40th percentile, I mean 40% of the data is to the left of it. So that tells you that there's 40% of the data in this area, or 40% of the possible outcomes are in this region here. So that means that this area is 0.4. That's the thing I know this time. And what I want to figure out is what's the base have to be to make that happen, right? So that's question mark. So the thing that I'm looking for there is my base. So let me just call this x. I'll call that little x since it's going to be a value of our variable, right? So if I call this little x, then I can say that, we're remembering that the height here is 1 over 90. So I can say that x times 1 over 90 has to be 0.4. Right? And then I solve this essentially, right? So I'm just going to multiply both sides by 90, and then we're good. So we go 90 over here, 90 times this, times 90. Here the 90s cancel, and so I'm just left with x equals 0.4 times 90, so that's 36. So that's so 36 seconds is the 40th percentile, which is to say 40% of drivers wait less than 36 seconds, and 60% of drivers wait more than 36 seconds. Yeah, that's percent. That's what percentiles are. All right, let's see what the other what the last question was. I think there's one more. Yeah, 5% of all drivers who stop at this stoplight have to wait longer than t seconds. Find t. So this is a very standard but confusingly worded question that you really have to think about. Right, so 5% of all drivers who stop at this stoplight have to wait longer than t seconds, and we want to find t. So let's go back to the picture. All right, so I'm looking for where 5%, well, I'm going to erase some of this stuff. All right, so I want to find where 5%, like the question is really, is it here or here? Right, that's really what the question is. And it says 5% of drivers have to wait longer than t. So what that means is that 5% is more than t. So it's over here, right? This is the 5%, and then this guy is 95%. So that means that I'm looking at t here, where this is 5%, 5%, and this is 95%. And you find that in exactly the same way as we did before, right? We're just going to do t times 1 over 90 equals 0.95, or t times 1 over 90. Well, I'll show you two different ways to approach it in just a second. But this is, instead of the 40th percentile, this is the 95th percentile. That's it. That's the only difference. I just asked it in a more confusing way. So let's erase this stuff. This works better with my finger. Let's erase that stuff. and do our calculation. And it's kind of more natural, at least in my opinion, to do this calculation from the right side. It's a little bit less mathematically simple, but it's not much harder. But it seems more natural to me to use the 5% than the 95%. But you can totally use either one. They're both fine. Heck, I'll just do both, right? So if I want to know what the length of this base is, it's 90 minus t, right? It's the right edge minus the left edge of the base here, times 1 over 90 equals 5%. So I can say that 90 minus t times 1 over 90 equals 0.05. And then we just calculate it up. So we have to distribute the 1 over 90 to both things. So this says 1 minus 1/90th t equals 0.05. Subtract 1 from both sides, I get negative 1 over 90t equals negative 0.95. The negatives cancel. And then 1 over 90t equals 0.95. So we get t equals 40 times 0.5? No, I forget what that is. So I'll just multiply 0.95 times 90, and we will see what that comes out to be. So let's calculate this. 0.95 times 90 gives me 85.5. There we go. What am I looking at? Whiteboard here. Yeah. Equals 85.5 seconds. And you could certainly do this the other way, where you do t minus 0. So t times 1 over 90 equals 0.95. And in fact, that just means that you start right here. And you start at this step right here, which is slightly more convenient, actually. It's a little bit more convenient to do it that way. It seems a little bit less natural to me because you have to first convert this from it's 5% in the problem. You have to think to yourself, okay, that means the 95th percentile. So I'm going to use the left side to do this, but works totally fine. You just start here and you get 85.5 seconds, of course. One thing I want to caution you about that perhaps I've chosen unwisely in my example is that these don't all start at 0. Like it's entirely possible to have a uniform distribution that starts at a different number. And let me very briefly do something like use an example of that, right? So let's say I had U 1050. I think this is the one I put on the review sheet. Let's add U 1050. So again, U for uniform distribution, 10 for the left endpoint, 50 for the right endpoint. So if I draw that, it's a rectangle, right? It's still a rectangle. It just goes from 10 to 50. 10 to 50 like this. And so if I wanted to find the, let's say the 60th percentile of this distribution, well, okay, so the length from 10 to 50 is 40 units. So that means that this height, it's not 50, right? It's tempting to think, oh, it's 1 over the right endpoint. It's not. It's 1 over the length of the base, and the length of the base here is 40. So this is 1 over 40 here. And then the 60th percentile, let's say this right here, we're going to call this thing X. The 60th percentile is still, so there's points, there's 60%. I made this really small. 0.6. I don't know why I made it so small. So there's 0.6 area over here. So what I'll do to find what X is I would do X minus 10, because that's the length of the base, times 1 over 40 equals 0.6. So you got to watch out for this, for it not starting at 0. It certainly might not, right? A lot of uniform distributions do because they're used for wait times a lot, and the wait times start at 0. But not universally. So you have to be a little bit careful about where the starting point is. So I might as well go ahead and solve this. Distribute the 1 over 40. Or actually, it's probably easier to multiply the 40 on both sides first. So I get X minus 10 equals 40 times 0.6 is 24. Then I add 10, right? So X is 34. So if it was 0 to 40, then the 60th percentile would be 24. But since it's 10 to 50, you have to add 10 to that to get 34 here, right? So we would say that 60% of the area in this distribution is less than 34, and 40% is greater than 34. So again, you don't want to think of everything starting at 0. They could certainly start at some number that's not 0. Could be negative as well, by the way. Like there's nothing saying these all have to be positive. All right. Let's go back to the notes and see where we're at. So That's all I want to say about uniform random variables. So just to sum up, they are used if every outcome in a certain range is equally likely, and oh no, wait, that's all I want to say. Every outcome in a certain range is equally likely. It's continuous, and and all the outcomes are equally likely. And the way you calculate them is all just a bunch of rectangles, right? It's all just base times height, very simple, right? So no complex calculations, really. You might have to think about how the questions are phrased, but the math itself is usually quite simple. Okay, let's get to one where the math is not quite as simple, and we'll need our calculator because everything's exponential here. Exponential random variables. So these are really interesting, actually. In the sense that, well, one, there are quite a few things in the real world that actually follow this distribution, which we'll talk a little bit about. But the important part, or the most important part of them, is their connection with Poisson random variables. Like if you remember Poisson back from discrete random variables, I mentioned that things with an exponential wait time give you Poisson events, and Poisson events have an exponential amount of, or exponential random variable amount of time between them. So let's see what those look like. So here is what your basic exponential random variable looks like. It is just an exponential function. This is, so the formula here that we're using is this one. If we wanted to graph it, y equals me to the minus mx for m some parameter, like depending on what thing you're finding the probability of. It's called the decay constant. This is just, if you think back to algebra, this is just your basic exponential exponential graph, right? This is just an exponential function with e to the power of something, right? E to the x. Yeah, so it turns out that a fair number of things follow this distribution. It's probably most commonly used as the wait time between between Poisson events, or the space between Poisson events, depending on what you're measuring. The notation for it looks like this: exp of m. So m is the decay constant, which is related to the mean of the distribution, which is 1 over m. Right. We'll talk about that in just a second, but this is another one where I can justify to you why the mean would be 1 over m. If you know calculus, I'll be happy to show you what's in calculus if you want. I can kind of hint at it. I can hint at why it's true. Let me graph something. Let's go back to the calculator, and I'll show you a little bit of a graph, or a couple of graphs here. Clear that off and go to y equals. So if I do like 3e to the power of 3x, or to the minus 3x, e to the negative 3x, and we graph that, you can see it drops quite sharply, right? It looks like it goes below the line and goes below the axis, but it never does. In fact, let's set our window here. Where's my window? I want x to go from like -1 to 10. That's fine. Y can go from -1 to like 5, something like that. Graph that. That didn't go down to -1. Oh, I put x scale as -1. Sorry, my bad. -1 to 5. That's what I meant to do. X scale can be 1. All right, let's try it again. Graph that. There we go. That's what I'm looking for. So you can tell this blue line goes down pretty sharply. It turns out it's because 3 is bigger than 3 is relatively large in this context. And so if I want to do like, let's do a half, right? So if I did 0.5 x, nope, that's not the right button for x. There's x. That's not what I wanted at all. Times e to the power of negative 0.5x, negative 0.5. Now I want the x. We'll see that, so the red line is that one. That goes down much shallower, right? It goes down quite slowly. and is very shallow. In fact, the y-intercept is the 0.5. It's the decay constant, right? The y-intercept here is 3. And so it's decreasing very slowly. So what that means is the mean for this one that goes down really fast is relatively small. Like the average value is relatively small because it gets down to the axis really quick. Whereas this red one, the mean is bigger. And so you can see that there's kind of an inverse relationship, or not kind of, there is an actual inverse relationship between how fast it decreases and where the mean is, right? So the bigger m is, the smaller the mean is, and the smaller m is, the bigger the mean is. That's what I'm trying to get at. That's why that inverse relationship exists that we can see right here, where the mean is 1 over the decay constant, where bigger decay constant makes it decay much faster, right? 3 made it go like almost straight down, 0.2 or 0.5 made it go really shallow. And you can see this one is a 0.25. So this one has a mean of 4, since the decay constant is 1/4, right? So yeah, and it turns out that the standard deviation is equal to the mean. That is not exactly a coincidence. That's not a thing that's generally true for continuous distributions, but it is true for this one, where the mean and standard deviation are equal. It's again, not a coincidence. It's just a artifact, I guess, of the way those things are calculated. Yeah, so this doesn't have a PDF or CDF in your calculator either. Like there's no exponential PDF, no exponential CDF. So we need a formula to calculate the area to the left or right of something. So here it is. I understand this is kind of hard to read. I'll show you what it means in just a second. Yeah, let's see what that looks like. I feel like there was something else I was going to say and I forgot what it was. So let's look at an exponential distribution. So we have this. I'm going to draw this real big so we get a nice big picture here. All right, so I'm going to call this is not the mean. This is just literally any point in the middle is k. To the left of k, in blue, we're going to have some area in blue, and then to the right, we're going to have area in red. This is blue area, so the probability that x is less than k is 1 minus e to the minus mk. So this is what I had on the notes. You can see it right here. Probability that x is less than k is 1 minus e to the minus mk. So this m is the decay constant. The k is whatever number that we had in the middle. That was where the vertical line was. And then e is the base of a natural log. It's the number e, the constant e that you've almost certainly seen in algebra or calculus in the past. If you haven't, well, I will show it to you. E, by the way, is a little bit less than 3. It's like 2.718. And more. It goes on forever. It's sort of like pi. It's irrational. And there's a button on your calculator. It's super important in math. We're not going to see why it's super important, which is kind of a shame, but it is. So the probability that x is less than k, so this blue area here, is that 1 minus e to the minus mk. The area to the right, probability that x is greater than k, is e to the minus mk, which we could figure out by doing the complement rule, right? So if I did this, if I did 1 minus e to the minus mk, what I would get is I would get 1 minus 1 plus e to the minus mk, right? I distribute the negative, and these guys cancel, and so I just get e to the minus mk. So I hope it makes perfect sense that if this blue area is 1 minus e to the minus mk, that the red area is e to the minus mk. It's actually easier to calculate if you do it the other way, right? Using the complement rule. If we start with this idea that probability that x is greater than k is e to the minus mk, then the remaining area is clearly 1 minus e to the minus mk. So there you go. that's how we're going to calculate areas, is we're going to figure out what the cutoff is, right? So if we're looking for the probability that x is greater than 18, then k is 18, and then we'll use this formula. If we're looking for the probability that x is less than 2, then we're going to use k equals 2 and use this formula, right? And so since you can't calculate even something in your head, calculator everything, right? So let's see what that looks like. All right, we did 9. All right, Juan has bought himself a new computer, and Juan is a bit computer savvy. He knows that the length of time that his hard drive will last, which is also called the time to failure, has a mean of 4 years and is modeled by an exponential distribution, which, by the way, this is actually this is one common usage of exponential distributions, is time to failure in complex machines, basically where, yeah, that's one common common usage for it. So capital X is going to be the amount of time that it takes for Juan's hard drive to fail. And so we want to find the decay constant M and the formula for X. And we'll draw it and do all that stuff. So we said that it has a mean of 4 years, right? The time to failure has, for this particular type of hard drive, the mean of that is 4 years. And so if we want the decay constant M, we're going to use this relationship here, mu equals 1 over n. Now, a thing that I have been constantly surprised that my students do not know is that if A is 1 over B, then B is 1 over A. Like if you say something like A is the reciprocal of B, that is not the thing I wanted. I wanted this. If I say that A equals 1 over B, and again, the easiest way to think of this is that A and B are reciprocals of each other. That's a terrible B. B, there we go. A and B are reciprocals of each other. Well, that also means that B is 1 over A. So if mu equals 1 over m, then m also equals 1 over mu. So if I have, or Juan has, I guess, that mean is 4, that means mu equals 4, then m equals 1/4. That's it. Right? So the decay constant and the formula for x are actually in this picture right here. M is 0.25, has a mean of 4. So mu is 4 in this case. So it's this thing. And if you want to see what the formula is, it's this with m, which is, which is 1/4 plugged in here. So it's y equals 1/4 e to the minus 1/4 x. Or if you prefer, 0.25. I don't care if you use fractions. If you use fractions or decimals, they're the same numbers. What's the probability that Juan's new hard drive fails within the first 3 years? All right, time to draw a picture. Within the first, I'm just gonna erase all this. All right, so let's write down the formula. Our formula is y equals 1/4 e to the minus 1/4 x. All right, so that's our formula, and m equals 1/4, m equals 1/4, and mu is 4. Our picture looks something like the one we just had, right? Decreases kind of shallowly. But one thing I should say about exponential distributions, this formula here goes from minus infinity all the way to infinity, but the exponential distribution itself only goes from 0. But it's 0 to infinity, it does not go negative. So the question here was, what is I forgot what the question was. It's the probability it lasts at least 3 years, fails within the first 3 years. All right. So lasts 3 years or less is the question, right? So I've got 3 here. There's 3. And I want to know what's the probability that we fall into this area here. Well, that is asking about probability that x is less than 3. And we know what the formula is. It's 1 minus e to the minus mk. So 1 minus e to the minus, and m is 1/4, and k here is 3. It's the cutoff times 3. So this is 1 minus e to the minus 3/4. That's the probability. We're just going to go jam that into our calculator and see what we get. So I'm going to do 1 minus e to the power of negative 3/4. And you can enter this as a fraction or a decimal at your option. Does not make any difference. There you go, 0.5276. Let's go put that on the worksheet, or on the whiteboard here. Great, let's see the next question. What is the probability that Juan's new hard drive lasts at least 3 years? Aha, we can answer this one without doing too much work. So if we're asking about at least 3 years, then we're asking about the area over to the right of 3, right? Well, that's just 1 minus the area to the left of 3. So if I wanted, let's do this. Probability that x is greater than 3 equals 1 minus probability that x is less than 3, which is 1 minus 0.5276, which, using our clever formula of 99910 here, so I want 4724. 0.4724. All right, great. That's how we do that question. Let's see what else we got. What is the probability that Juan's new hard drive lasts at least 5 years and then between 3 and 5 years? All right, so it lasts at least 5 and then between 3 and 5. So at least 5. So I'm going to go ahead and erase this blue stuff. Not that it's not important, it's just not relevant to us right here. So at least 5. So here's 5. That's not intended to be blue. Let's go ahead and undo that. Make it black. There's 5. Okay, so 5. So the probability that Juan's hard drive lasts at least 5 years, we'll make that one red, is going to be, using our formula, again, so we've got k equals 5 here, so I'm going to do probability that x is greater than 5 is e to the minus mk, so e to the minus 1/4 times 5. All right, so m is still 1/4, k is in this case 5, and we just jam that into the calculator, and we get e to the negative 5/4. So let's go up. E to the power of negative 5/4. 0.2865. Great. Go back here. 0.2865. All right. So now the question that we asked for the final part was, what's the probability that we are between 3 and 5, right? So this. So there's a couple ways we can find that. I think the easiest one is to take the area less than 3, area greater than 5, and add them up, and then subtract that from 1, right? Because I want to find the green area, I want to take off this area and this area. So probability that 3 is less than x is less than 5 is 1 minus probability that x is less than 3 plus probability that x is greater than 5, which we will go ahead and calculate that up. 5276 plus 2865. Oh, I can just add those together. Great. Plus 0.5276. 8141, 0.1841. So I'm 0.8141. So I'm going to do 1 minus answer, minus, not times. And again, I don't know if you guys have seen this or if you remember this, but the negative key on your calculator, the second function of that is answer. So it'll just, if I do 1 minus the answer, get that, 0.1859, which I could have done very easily by subtracting this from 1, right? Like 9, 9, 9, 10. So I need 1, 8, 5, and then 9 to make 10. So 0.1859. All right, let's go put that on our whiteboard. 0.1859. Thereabouts. And there we go. So let me emphasize a couple things. One, drawing a picture, really helpful, right? Being able to point at an area and say, I need to find this area is really, really helpful, especially if you have that that picture in your mind with decay on it, right? With the 1 minus e to the minus mk to the left and the e to the minus mk to the right. That makes it much clearer about how you, about what formula you want to use. Secondly, you can use the picture to divide up the area that you're looking for, or divide up the area under the curve into pieces that you are looking for. And it is much more obvious when you might want to use the complement rule, right? Like it's probably not immediately apparent to you that, at least without a picture, that the opposite of x being between 3 and 5, or the complement of the probability that x is between 3 and 5, is 1 minus the complement, or 1 minus the probability that x is less than 3 plus the probability that x is greater than 5. But that is what it is. And if you look at the picture, it's obvious, right? So this area is the whole thing, which is 1 minus this and minus this, right? Pretty obvious from the picture. So the picture does a really good job of helping you solidify in your mind what formulas you should use. So it's a visual aid, really, that's what it is. I recommend drawing pictures for basically everything. Yeah, that's, I think I want to end the statement there. I recommend drawing pictures for basically everything. You will see me draw pictures for like essentially everything I ever show you how to do on a probability distribution. So yeah, I think that's all I want to say about that. So let's go back to the notes. Notes here. Yeah, let's do this one. I usually skip this one in class, but there's no really upper limit on this time. So I'm going to talk about this for the next couple minutes, and then talk about the relationship between exponential and Poisson distributions. So if we know that Juan's hard drive is already 5 years old, what's the probability that it will last at least 3 more years? So in other words, what if we know that it's already 5 years old? So given that x is greater than 5, so that its lifetime is greater than 5 years, what's the probability that it will last at least 3 more years? So at least 8 years. So we're going to do that in the same way. So probability that x is greater than 8, given that x is greater than 5. So we're going to do that the same way we do every conditional probability. So let's go look at this. I'm just deleting everything. Okay, so, oops. There we go. Okay. Same picture, but not in green. Nothing wrong with green, just it's a little rough on the eyes. I want that as a highlight color. There we go. So this is still Juan's hard drive, so this is still y equals 1/4 e to the minus 1/4 x. And our question was, given that it has lasted at least 5 years, what's the probability that it will last at least 8 years? So probability that x is greater than 8, given that x is greater than 5, would be the probability that x is greater than 8 and x is greater than 5, divided by the probability that x is greater than 5. Now, a thing that's maybe not immediately obvious is that x is greater than 8 is included within x is greater than 5. So if like anything that's over here, any x that's larger than 8 is also larger than 5. So this top bit is equivalent to saying x is probability that x is greater than 8. right? Because if it's a greater than 8, it's automatically greater than 5, but not vice versa. So if I want to find the probability that x is greater than 8, that is going to be e to the minus 1/4 times 8 over e to the minus 1/4 times 5. Now, we can jam this in the calculator if you would like to. I will do so in just a second, but I want to note that this is just basic exponent rules. So what we've got here is like bases, and so since I'm dividing them, I should subtract the exponents. So this top one is e to the negative 2, and this is e to the negative 5/4. So what I should really do is this is e to the numerator minus 2 minus a minus 5/4, which is e to the negative 3/4. And e to the negative 3/4, if you recall, is what we got. Well, we didn't actually do that one, but here, let's do that. So if we do e to the negative 3/4, e to the negative 3/4, we get that. We actually did this one using the complement rule, but 4724, 0.4724. If we were to calculate the probability that x is less than 3, what we would do would be 1 minus, that x is greater than 3. What we would do is we would calculate e to the minus 3/4. It's literally the same calculation. So what that means is the following. What we have is that the probability that x is greater than 3 is the same as the probability that x is greater than 8, given that x is greater than 5. And in fact, that would be true for any choice of years that were 3 apart. What this means in terms of like this question is that the probability of Juan's hard drive lasting at least 3 more years is constant at any point in time. This property is known as memorylessness. So in other words, this distribution is memoryless. It does not remember what has happened before where it is now. The probability of lasting 3 years is always the same. It's kind of interesting. I don't know of any other distributions that have this property. I'm not sure any other ones do, because you would need to have this relationship where you'd have something like, you need to have this relationship where like the probability that x is greater than k is equal to the probability that x is greater than a plus k, given that x is greater than k, right? Which is, I'm not sure, shared by any other distributions that I know of. But that's this property. It's kind of interesting. All right, back to the notes, and then we got one last thing to talk about, and then we're done. Well, anyway, that's before I do that, let me sum up exponential distributions. For exponential distributions, they always decay. You start at 0, right? Let's start at x equals 0, and they go to the right forever. So there's no upper limit on an exponential distribution. There is a lower limit of 0. They decay exponentially, which is to say they have a formula that looks like this. The m is your decay constant, determines how fast your graph goes down towards the axis. The bigger m is, the faster it gets down there, like an m like 10 goes almost straight down, and then levels off really sharply. And a small m decays really slowly like this. The mean and standard deviation are both 1 over m. And here's the notation that we use. X is approximately exp, so yeah, exponential with decay constant m. Then your formulas are these guys: 1 minus e to the minus mk to the left, e to the minus mk to the right. Okay. So the relationship between exponential and Poisson distributions is that if you have Poisson events separated in time, so for instance, industrial accidents, let's say, let's say, at this one factory you have an industrial accident. On average, like the lambda for your Poisson distribution is like 1 every 2.5 years, right? So 0.4 industrial accidents per year. Well, the wait time between those events follows an exponential distribution. So the events themselves are discrete, but they're dividing up time into chunks, and those chunks are continuous, right? Because they're measuring time. And the distribution that those chunks of time follow is an exponential distribution with m equals lambda. So the average size, so the mu is 1 over m. So the average amount of time between events is 1 over the frequency of the events, which is lambda. So let's see how we can use this. All right, we're going to count 2 different random variables. We're going to call them x and y here. So particular call center, each operator, oh, by the way, the title of this is, I used to work in a call center. It wasn't that much fun. At a particular call center, each operator handles an average of 20 calls in an 8-hour workday, which is to say 20 over 8 calls per hour. Number of calls in any particular period of time follows a Poisson distribution, and the average time between receiving calls follows an exponential distribution. So we're not worried about the amount of time that the call itself takes, only the amount of time from the start of one call to the start of the next call. All right, so start of one call, start of the next call. It ends somewhere in here, but we don't care where. I just care how long this time is. Let x be the random variable that counts how many calls a particular operator takes. Notice the how many telling you discrete. That's going to be the Poisson distribution. And y be the random variable that measures the amount of time between the start of one call and the start of the next. So measuring an amount of time, you would say how much time has passed, right? So that's the continuous one, that's the exponential distribution. So find the relevant parameters, write down the probability distributions of x and y. All right, let's go ahead and do that. So I'm going to pop over to the whiteboard here, clear everything off. You can say that they handled 20 calls in an 8-hour workday. Right, so the average number of calls, what is it, 2.5 per hour? Yeah. So if I do 20 over 8, I'll get 2.5. Right, so this is 2.5 calls per hour on average. Right, so if we're measuring calls, or if we're measuring lengths of time in hours, our lambda is going to be 2.5. So that means that x, the Poisson, or the discrete random variable, is approximately Poisson of 2.5. And y is approximately exponential with the decay constant of 2.5. Right, so this is why it's really important to pay attention to what goes in front of the parentheses. It tells you what distribution you've got. So x is a Poisson distribution with 2.5 calls per 1 hour, and y is an exponential random variable with a decay constant of 2.5, where you have m equals lambda. Write down the probability distribution. Okay, we did that, great. Find the probability that in a particular hour, the operator takes 4 calls or less. I should say fewer. That word should definitely be fewer. Sorry, that's not great grammar there. So in a particular hour, the operator takes 4 calls or fewer. Now, notice that we are counting number of calls here. So that is x, right? That's what x counts. X is counting number of calls in an hour. So that is not the share I was going for. Let's go for the whiteboard. So I can say the probability that x is less than or equal to 4, I think, 4 calls or fewer, equals, well, I'm going to use my calculator. I'm going to use Poisson CDF of 4, right, where lambda is 2.5. Of, I don't remember what order it goes in. I think 2.5 comma 4. Let's go look in the calculator. So now I actually do want that calculator share here. So we're going to do Poisson CDF. So that is in distributions. Go down to Poisson CDF. Notice I'm not using PDF because I'm not doing equal to, I'm doing less than or equal to. So I want CDF. Mu is 2.5. X value is 4. Paste. So we've got 0.8912, which makes perfect sense, right? If the average number of calls in an hour is 2.5, it's quite likely that you're going to handle 4 or fewer, right? Like you usually handle 2.5. So handling 4 would be a lot. So 4 or fewer would be totally normal. So 0.8912. Where am I at here? About equal to 0.8912. All right, let's see what the other question is. Where is it? There it is. Find the probability that the time between the start of 2 calls is less than 30 minutes. Now, again, I'm expecting this to be relatively large, right? Because you like handling, if the, how can I say this? The wait time between, if the length of, you handle 20 calls in an 8-hour workday, you're handling more than 2 per hour, handling 2.5 per hour on average. So this wait time of 30 minutes would be 2 per hour, right? That's the rate it would be. So I'm expecting this number to be relatively large, right? The probability that you're going to handle more calls than that, or that the wait time is less, should be relatively big. So let's go see what that looks like. I'm going to draw a picture. Start between the start of 2 calls is less than 30 minutes. All right. So for this one, we're using the exponential because it's measuring the wait time between the starts. This is y equals 2.5 e to the minus 2.5x, right? M is equal to mu. And the question is, what's the probability that we get less than 30 minutes in here? Now, a tricky thing that I have done is I have switched units on you from hours to minutes. So since I want 30 minutes, that's half an hour, right? So the mean here is 40, or 40, is that right? No, 20 minutes. Yes, means 20 minutes. So what I want is the probability that y is less than 0.5, not 30, right? Because this 2.5 is in hours, that's calls per hour. And so I need the number, I need the number of hours for the wait time, and 30 minutes is half of an hour. So you have to make your units consistent. So I'm not using 30, I'm using 0.5. So the probability that y is less than 0.5 equals, well, the left side is 1 minus e to the minus mk. So I'm going to do 1 minus e to the minus, m is 2.5, 2.5 times k, which is a half. Right, so that's what I'm going to do. And of course, jam that in the calculator. So you can do the 2.5 times 0.5 and get 1.25 in your head, but I'll just type it in like I would expect most students to do. Oop, not that yet. So I'm going to do 1 minus e to the power of negative m times k. That was 5. All right, and I get that. So 71%, so pretty likely. It's likely to take less than half an hour between like the time when you start one call and the time when you start the next. So 71.35%. It's at 135. And there you go. I will put an extra credit question on the test involving this. So if you'd write it down, I know it. Yeah, I think that's all I want to say about that. So that's the relationship between Poisson and exponential, is that Poisson random variables have a wait time that is exponentially distributed, and things with an exponentially distributed wait time follow, like the events themselves follow Poisson distribution. So there you go. All right, briefly sum up. I don't want to sum up too much here. Got my summary at the end of the notes. Feel free to browse through this. This is a really important idea. The way we find geometric probability, or probability when we have like a picture or a graph, is that it is the area we're interested in divided by the total possible area. And then we've got two specific random variables. So yeah, I think we'll call it there. That sounds like everything I wanted to say. So I'm going to go ahead and stop the recording now, and I will see you in the next.